May 15, 1943, the North Sea, 11 nautical miles off the Danish coast. The gray water churns beneath an overcast sky as U-boat 447 cuts through the waves at periscope depth, her commander scanning the horizon for Allied convoys. The diesel engines hum their familiar note, a sound that has carried this iron vessel through 4 years of war. Below deck, the crew moves with the rhythm of routine, men who have survived countless patrols, countless close calls with depth charges and ramming attacks. They believe themselves invincible in these northern waters. They believe wrong. Somewhere in the water ahead, invisible, silent, something waits. Not a ship, not a net. Something that listens. Something that remembers sound. Something that will, within the hour, transform this vessel and her 73 crew members into wreckage settling through cold water toward the seabed. No warning shot. No sonar ping. No human decision to fire a weapon. Just the simple, innocent act of existing, of keeping her engines running, has triggered her own destruction. This is the story of the Acoustic mine, Britain's deadliest maritime weapon against the U-boat fleet. A weapon so clever, so perfectly engineered, that the enemy barely understood what was killing them even as they died. The Acoustic mine represented something revolutionary in warfare. A weapon that required no human operator, no luck, no conventional targeting system. It simply listened. In an era when German U-boats dominated the Atlantic, when convoys were being torn apart faster than they could be replaced, when British naval operations seemed locked in an endless, draining stalemate, desperation bred innovation. The Royal Navy faced an impossible problem. German submarines operated with almost perfect safety in deep water. Traditional magnetic mines could be swept. Moored contact mines caught nothing. Anti-submarine vessels and aircraft were desperately stretched fighting the constant tide of new German boats entering service. What Britain needed was something that could identify a U-boat by its unique acoustic signature and react instantaneously, without human intervention. Something autonomous. Something that could hunt beneath the waves with the precision of a predator that never slept, never tired, never made a mistake. The numbers tell a grim story of Allied desperation. During 1942, German U-boats were sinking approximately 200,000 tons of shipping per month across all theaters. The British Admiralty was losing the war at sea. Production of new merchant vessels could not keep pace with losses. Naval escorts were stretched impossibly thin. The morale effects were catastrophic. Sailors volunteered for convoy duty knowing their odds of survival had become genuinely poor. Britain was being slowly strangled, her lifelines cut one by one. The Americans, entering the war with fresh resources, could throw numbers at the problem, building Liberty ships at astonishing rates and deploying thousands of naval vessels. Britain had something different to offer: brainpower, desperation, and institutional knowledge accumulated across centuries of naval warfare. What the British needed was multiplication, a way to make their scarce naval assets infinitely more effective by letting machines do the hunting while sailors rested. The Acoustic mine represented the embodiment of that principle. Intelligence engineered into metal and explosives, distributed across vast areas of ocean, never forgetting, never resting, waiting patiently for the moment when a target entered its domain. The technical challenge was profound. Submarines generated distinctive acoustic signatures at different speeds. A U-boat running at slow patrol speed produced a different acoustic pattern than one at periscope depth or at maximum depth. German vessels used multiple engine configurations depending on the tactical situation. British mine designers needed to create a device that could distinguish between the acoustic characteristics of a German U-boat and those of innocent vessels, Allied ships, fishing trawlers, even whales. The solution emerged from research undertaken primarily at HMS Collingwood near Gosport and the Mine Design and Development Establishment. Engineers, many of whom had previously worked in civilian acoustics research or telephone engineering, approached the problem with methodical ingenuity. The core innovation was the development of a resonance frequency detector that operated on a principle of mechanical tuning. Inside the mine's casing, protected from water pressure, sat a series of acoustic sensors coupled to metal diaphragms tuned to specific frequencies. These frequencies corresponded precisely to the propeller vibration patterns of diesel-electric U-boats operating at typical cruising speeds. The mine itself, roughly the size and weight of a standard contact mine, approximately 1,500 pounds or 680 kilograms, could be deployed from naval vessels, modified destroyers, and later from high-altitude bombers. Its construction represented a fascinating marriage of brute mechanical engineering and precision manufacturing. The outer casing was cast steel, capable of withstanding water pressure at depths exceeding 300 meters. Within this protective envelope sat the acoustic sensing apparatus, an arrangement of hydrophones connected to amplifying mechanisms that operated on vacuum tube technology. The innovation that made everything functional was the acoustic fuse itself, a device that would translate waterborne sound vibrations into electrical impulses, amplify those impulses, and, when they matched the preset frequency pattern, trigger a relay mechanism that would fire the explosive charge. The responsiveness was extraordinary. From the moment a U-boat's distinctive acoustic signature entered the mine's detection radius, estimated at roughly 1,000 to 2,000 meters depending on water conditions and the boat's speed, the mine's electronic systems would begin their lethal calculus. There was no decision process, no human element, no opportunity for evasion or negotiation. The mine simply responded to a physical stimulus with mechanical certainty. Manufacturing these devices required precision machinery and skilled craftspeople. Wartime production was distributed across multiple facilities, including the Grange Road Ordnance Factory in Coventry and various naval installations. Estimates suggest that approximately 500 to 1,000 acoustic mines were manufactured throughout the war, though exact figures remain classified in certain archives. Deployment began in earnest during late 1943. Large minefields were sown across the waters around Denmark, along the Norwegian coast, and in the approaches to German-occupied ports. One of the most significant operational deployments occurred in the Great Belt, the straits separating Denmark and Sweden, where German U-boats were forced to transit regularly. The operation, conducted throughout the winter and spring of 1943 to 1944, proved devastatingly effective. U-boats began encountering mines in positions where the German High Command was convinced no mines could possibly exist. The sinkings defied the standard German model of submarine warfare. These were not the dramatic explosions of conventional mines triggered by metal contact, nor were they the chaotic disorder of depth charge attacks. Instead, U-boats were simply disappearing, lost to what survivors could only describe as catastrophic internal explosions. The acoustic mines created a psychological impact that far exceeded their raw material impact. German submarine commanders reported feeling hunted in waters where they had previously felt safe. The speculative discussions about whether the British possessed some entirely new technology, electromagnetic detection systems, perhaps, or some form of directed energy weapon, began to circulate through the German Navy. This psychological dimension was perhaps as significant as the physical destruction. Uncertainty became a weapon in itself. If you are finding this interesting, a quick subscribe helps more than you know. It genuinely does affect what we can create next. The German Navy attempted various countermeasures. They developed ships designed to sweep acoustic mines, equipped with devices that would produce constant noise designed to trigger the mines prematurely. These vessels, known as Linsengerät, or lentil devices, operated with limited success. The German approach to acoustic minesweeping was fundamentally reactive rather than proactive. They lacked the deep understanding of exactly how the British system functioned, which placed them at an enormous disadvantage. By comparison, the American approach to mine warfare remained more conventional, relying primarily on magnetic mines, contact mines, and in later stages, anti-submarine engineering integrated into coastal defense systems. The Americans possessed the industrial capacity to produce mines in extraordinary quantities. Estimates suggest roughly 34,000 mines were laid by the Allies in European waters during the war. However, the acoustic mine represented a qualitative difference from these quantitative approaches. It was not a measure of abundance, but of cleverness. The British acoustic mine outperformed German attempts at acoustic minesweeping by a factor that German engineers found baffling. Every countermeasure they attempted seemed inadequate. Their sweepers would trigger mines at the wrong times, clearing paths only to have those same paths mined again within days. The technological advantage accumulated with each failed attempt at solution. The actual impact of acoustic mines on the final outcome of the U-boat war remains genuinely uncertain. Records are fragmented, and much remains classified in both British and German archives. What can be stated with confidence is that acoustic mines contributed to the rising U-boat casualty rates during 1943 and 1944. Whether they were responsible for the sinking of 5 U-boats, 15 U-boats, or some other number cannot be definitively established from publicly available sources. What is clear is their symbolic impact. They represented the point at which the technological tide had definitively shifted against Nazi Germany. The U-boat, the weapon that had brought Britain to the brink of starvation, was now hunted by machines that never slept. The psychological effects on German submarine crews became measurable in operational reports. Men who had volunteered for submarine service in 1939 with the expectation of glory were by 1943 and 1944 experiencing something closer to despair. The acoustic mine was part of a broader arsenal, including improved depth charges, radar-equipped aircraft, and coordinated convoy tactics that collectively transformed the Atlantic from German hunting ground to German graveyard. One surviving example of the acoustic mine can be encountered at the Royal Navy Submarine Museum in Gosport, the very town where much of the development work took place. The device sits in a display case, its cast steel exterior worn by decades, its once secret mechanisms now openly exposed to public view. Reading the accompanying plaque, visitors confront the reality that several U-boat crews entered the water believing they had simply encountered bad luck, not comprehending that they were destroyed by a weapon that defined a new category of naval warfare. The acoustic mine also influenced post-war maritime doctrine across multiple navies. The Soviet Union obtained examples through various means and adapted them for their own purposes. The United States experimented extensively with acoustic mine designs throughout the Cold War, eventually developing far more sophisticated systems. Modern mines still incorporate acoustic elements in their detonation systems, a lineage that traces directly back to these wartime devices. The innovation lived on, mutated, became ever more sophisticated, but the fundamental principle remained unchanged: a weapon that listens, that remembers, that executes its purpose with mechanical precision. The acoustic mine stands as a pivotal example of innovation born from desperation. In 1942, Britain faced imminent defeat through naval blockade. Conventional countermeasures, whether ships, aircraft, or depth charges, proved insufficient. The British innovation was not to throw more ships at the problem or more sailors into harm's way. Instead, it was to engineer intelligence directly into the seabed itself. To create artificial hunters that required no human guidance, no human risk, no human cost beyond the initial investment of engineering talent. In a war that had become bogged down in mutual slaughter, in which millions of soldiers had become casualties in attempts to achieve marginal gains in ground or sea control, here was a war-winning technology born not from industrial quantity but from intellectual quality. The acoustic mine represented the point at which scientific sophistication could substitute for brutal attrition. And though the actual body count it achieved remains obscured by classification, though historians continue to debate its precise impact, the principle it embodied proved revolutionary. In the decades that followed, as navies equipped themselves with ever more sophisticated autonomous weapons, from mine systems through to modern anti-ship missiles, they were following a path laid by the Acoustic mine in the North Sea, 1943. A path that suggested that the future of warfare belonged not to the most numerous, but to the most clever. That machines could hunt as effectively as men. That intelligence, properly engineered, could become a multiplier of force that no amount of conventional weapons could match. The Acoustic mine proved all of this in the gray waters off Denmark, where it waited in patient silence, listening always, striking without warning, a warning to any enemy foolish enough to believe themselves safe.